Okay, number 65, we're given two coils. The inner one has a current going around, if we're looking downwards, obviously, it's the counterclockwise direction, and the outer coil has a current going in the clockwise direction. We're given values for these currents as well as lengths for their radii. And then we're asked to find magnitude of B and the direction of B at the center of the coils. After which we're asked to vary R2, let R2 vary, and then we can find the value when the B field goes to 0. We'll get to that in a minute. So, okay. Just checking everything here. So, okay, good. Now we can actually use this formula that we tried a couple times that didn't quite fit into our problems before, but we know mu naught, we know I, we know the radius, right? So we can plug these in. Okay, well, the number of turns is 1, right? These are just single coils. And so now we're going to use what we call superposition, which is pretty much just summing up our B fields. And we want to note that the B field for current 2, if we look up here, for current 2, it's coiled along this direction. So if you wrap your fingers around your right hand, the fingers of your right hand in this direction, your thumb will point straight up. So B field 2 is coming in the positive Z hat direction, straight out of the page, which means that the B field for our other current is going to be going in the opposite direction. And again, in order to wrap our right hand fingers around this way, we have to flip our hand over, curl our fingers, and the thumb will be pointed downwards into the negative Z hat direction. So that's useful. And now we take B net is equal to, we want to say mu naught over 2. And we're going to have 3 amps over 9 centimeters. And then our negative for the other current, 5 amps over 0.12 meters. And then we simply plug these in. By the way, this is Tesla meters per ampere. Meters cancel, amperes cancel. We're left with Tesla, which is what we want. And that's going to give us a value, negative 5.236 times 10 to the negative 6 Tesla. Otherwise, we can write this down as Z hat. So this is 5.24 micro Tesla in the negative Z hat direction, which is into the page. So that's the B field at the center of these two coils. All right, and now we want to find, we want to change our value for R2 so that the B field's going to go to 0 at the center. So what that means is we have our B net times mu naught over 2, just like before. Then we have I 2 over R2 minus I 1 over R1. And we want this to go to 0. So we set this to 0. Well, right away, these are going to go away. Those factors cancel, right? And we're left with I2 over R2 is equal to I1 over R1. Okay, and we want to know what the value of R2 is, so then we just solve for R2. So we take this over here, we take these guys over here, and then we're left with R1, I2 over I1. What does that equal? That equals, we have 3/5 times 0.12 meters equals 0.072 meters, or 7.2 centimeters. So for B to go to 0 at the center, R2 must equal 7.2 centimeters. let's see. Was that? Okay, we'll do the next problem then. So we're given a wire with a current, and then we're given a rectangular loop, conducting loop with also a current, and the currents are going in a similar direction here. We're told this length. We're told the length of the rectangle is 0.45 meters. We're told the width is 0.15 meters, and then C, the distance between them, is 0.1 meters. We're also told that this is 5 amps and this is 10 amps. We're asked to find the force exerted by the wire on the loop. Okay, so let's recall that we have force from a current carrying wire is going to be the B field times the current times the length times the sine of the angle between them. So in our case, this is going to be, let's call this B1, because we actually have two different things going on, right? We have two currents, so this is a little different than before. So B1 times I2, this is how I'm going to label this, times sine of the angle, where B, called B1, is going to be the current 1. This is the force from here, right? Current 1, 2 pi r, where r is the distance to the wire. It's the distance between them. This would be the r here. Okay, so then we plug this into our force equation. 2 pi r times I1 times I2 times the length. Okay, now we want to look at, before we start plugging things in, we want to actually look at what directions things are going, right? So we have a current going upwards. If we point our thumb along that, then our fingers will curl around it, this direction. So then we have our B field kind of pointing directly in here from the wire. From the top, we're actually, yeah, so from the top and the bottom, these are going, the magnitude of this on both of these will be equal and opposite, right? This is going this direction, this is going this direction, these things cancel. So we don't have to worry about those. However, because the distance changes from here to here, so from the wire to the first wire, from the wire to the second wire, in the loop, right? Those are going to be different values. So we want to consider those two, okay? Okay, so now we want to use the right-hand rule to determine which direction the forces are actually going to be pushing. So we want to take I cross B, so the current cross the B field. So then we take right-hand fingers, point them in the upwards direction. The B field is going to be pointing inwards from here. I don't know why I have two things. So on this side, to be more explicit, we have this B field, it's pointing inwards, right? Into the page. That's what I mean to say. So right-hand fingers up, curl them into the page, and you're going to be left with your right thumb is going to be pointing in towards the left. Okay, we do the same thing over here. Right-hand fingers go down along the current, and then they curl towards the B field, which is going to be going also into the page, and then your thumb will be pointing to the right. Right, and so then I wrote this down a little bit. Again here, same thing. Current cross the B field gives you force this way. Current cross the B field here gives you a force this way. So what that means is now we can write down our force equation. Mu naught over 2 pi times L, which was 0.45 meters, and then so we're going to go current current 1. Current 1 over this distance here, right? And we're also going to have, so for this force, it's current 1 over this distance, and for this second force, it's current 1 over this whole distance here, because we're taking the force from this wire on these two wires. So I1 over C, I1 over C plus A. So what that looks like is this. Plus I1 over C plus A, and this is all times I2. Okay. Now let's recall that the direction of this one here is actually going to be pointing in the opposite direction of this one. So the one towards the right is negative. We'll call this positive. Right? So then I1 over C minus I1 over C plus A times I2. So that looks like mu naught L I1 I2 2 pi 1 over C minus 1 over C plus A, to make it as simple as possible. And then now you can just plug all these values in. You know what AL is. You're given this value, this one, and this one in the problem. You're given these values in the problem, so you plug them in. Check your units, and then we are left with 2.7 times 10 to the negative 5 newtons towards the left, where we identified left as the positive direction. Okay.